All right, welcome you guys to section 8.2. So we're going to talk about arithmetic sequences and series. So an arithmetic sequence is a sequence where you're adding or subtracting. We don't frame it in terms of subtraction. We would always frame it in terms of addition. So you would be adding a negative in that case. But to give you an example, something like this would be an arithmetic sequence, because each time it has to be the same thing that you're adding. We're adding 3. To get from 5 to 8, we added 3. We added 3 to get from 8 to 11. So the number that you're adding every time is called the common difference, and we use the letter D for it. Okay, if we had been subtracting 3, then the common difference would have been a -3. Okay, but we'd still frame it in terms of addition. So it's called the common difference because if you were to take any successive terms, so let's say you took like the second term minus the first term. So in other words, 5 minus 2, you get 3. If you took the third term minus the second term, so 8 minus 5, you get 3. You took the fourth term minus the one before it, so 11 minus 8, you get 3. So you can see that when you subtract, in other words, when you take the difference, you're always going to get a common result, the same result each time. So it is the common difference. In the next section that we're going to do, it's going to be called the common ratio. And we'll talk more about that when we get there. So there is right here the formula. Now I put here it's a sub 2 minus a sub 1. That's the one we use most frequently. But clearly you could see that any term minus the one before it or minus the previous term will work. Okay, so for each sequence, determine if it is arithmetic. If it is, identify a sub 1 and D, difference. Okay, so let's see what's going on each time. So to get from this one to the next, we added 5. And it looks like we added 5 again and added 5 again. So it will be arithmetic, okay? So it is arithmetic. Let's see if I can write the neatest. It's arithmetic with a sub 1, the first term being 3. That's our first term. And the common difference, the amount it's going up by each time, or what we're adding each time is, whoa, not 3. I'm thinking of the last example, you guys. It's 5. All right, let's look at this next example. Okay, so we do have to make sure that we're adding the same thing every time. Okay, now it's really hard to see what we're adding in this one. But remember, we do have a way to find the common difference. The common difference can be found by taking the second term minus the first term. So if we take 1/10 minus 3/5, that should do it for us. So we are going to have to multiply by 2 here to get the common denominator. So we've got 1/10 take away 6/10, which will get us -5/10, or in other words, -1/2. Now, I'm not sure if that's the common difference because I have to make sure that that's what's being added every time, right? Okay, so we know that from here to here, we subtracted 1/2, right? Or added a -1/2, okay? But we have to see to get from 1/10 to -2/5, did we also subtract 1/2? So let's go see. So 1/10, like the other way, 1/10 minus 1/2. Oh my goodness, I didn't get out of the denominator. So I don't use calculator very often. All right, minus 1/2. That got us -2/5, right? So it did work. When we subtracted 1/2 from this one, it gave us -2/5. So it looks like it's doing the same thing every time. Remember, an arithmetic sequence has to be adding the same number every time. And we were adding -1/2 each time, or subtracting 1/2 each time. Another thing that you could do just to check is you could say, okay, well, let me take the third term minus the second term and see what happens when I do that, right? And so if you do that, do you get the -1/2? Clearly you're going to. So -2 divided by 5 I'll remember to get out this time. Minus 1/10. There you go. There's your negative 1/10. Okay, so it is arithmetic because we're getting that same result, whether we do the second minus the first or the third minus the second. Okay, so it is arithmetic. With a sub 1, the first term, being 3/5, and the common difference d being a negative 1/2 this time. Okay. All right, let's try the next one. So on this one, we aren't adding the same thing each time, because to get from 2 to 4, we added 2. But to get from 4 to 8, we actually added 4. So this would not be an arithmetic sequence. Oops. We do have a name for this type of sequence where we're multiplying by the same thing every time, and that's what's coming up next. All right. Let's see here. Now, sometimes it's hard for me at the beginning of a sequence to see what the common difference is because the numbers are bigger in this case. So sometimes I'll check later on, like I'll be like, well, I can tell that from 27 to 20, I went down by 7. And I can tell I went down by 7 again, right? And so it's a little bit easier to see the -7 if you look further along. And that's fine. You don't always have to look at the first two. So if you can go down to these smaller numbers and spot it, perfect. You don't even have to bust out that formula where you take the second term minus the first term. What's that? 27, take away 34. Formula's there if you need it, but honestly, a lot of times you are just going to be able to spot it's -7. Okay, so this one is arithmetic. With the first term being 34 and the common difference being -7. Now, as for the word arithmetic, my understanding is that if it's a modifier, like an adjective, it's an arithmetic sequence. You say it as arithmetic. But if it's the noun, like I took arithmetic, you would say arithmetic. So if you're like, wait, I've always known that word as arithmetic, that's my understanding of it, you guys. Yeah. All right, so here's some formulas for finding the nth term of an arithmetic sequence. And so I'm giving you one here that's more general. I haven't seen this in a textbook. I don't know why. So I've just kind of put it in here because I think it makes some of the math easier on some of the other problems. But yeah, so we have this first term where, or this first formula where it's given to us in terms of the first term, but I generalize it down here in terms of any term. And that's the difference. So basically everywhere where you see a 1, it just becomes an n. I'm just going to highlight that so our eyes really see that. So anywhere in the formula where there was a 1, it's now going to become an n and nothing else changes. Okay. All right. So to kind of, now if you're not somebody who's into proofs, you know, I'm going to put chapters in here, skip to the next one. Okay. But if you're somebody who's planning on majoring in math, or you just like to see why things work, then go ahead and stay tuned for this. It's good that we get that exposure to proofs because all you're going to be doing in your math degree is proofs, and you don't want to come in and just get slapped in the face with them when they're, you know, higher level thinking. It's nice to do these other ones along the way. Okay, so if we have an arithmetic sequence, then the first term in our sequence is called a sub 1. Then to get to the next term in our sequence, we'd have to add the common difference. So we would have to add d. So that means that the second term in our sequence, a sub 2, would really be a sub 1 plus d. So far we have that the second term is a sub 1 plus d. Now, if we continue this trend and we want to know, okay, well then what's the third term? Well, we know we're adding d every time. So we would just have to add another d to get from the second to the third. So then that means it would be a sub 1 plus 2d's this time. So the third term is a sub 1 plus 2d's. And you can probably, some of you see where this is heading already. I'll probably just do one more so we can really see the pattern. But to get to the fourth term, we would just have to add another d. And so this one would be a sub 1 plus 3d, etc. Okay. So the fourth term is the first term plus 3d's. So what I really want you to look is I want you to notice, I'm going to put a 1 right here. This is a 2, this is a 1. This is a 3, this is a 2. This is a 4, this is a 3. Hopefully you're seeing that the number over here in front of the d is 1 less than the number over here, okay? So what that means is if we were to try and generalize this and find, let's say, the nth term, well, we know it's going to be a sub 1 plus because they're all a sub 1 pluses, okay? We just have to figure out how many times we're going to add the d to it. Well, you can see from what I've highlighted in orange, it should be 1 less than the number over here. Well, 1 less than n is n minus 1. And that is the formula that you see given right here. Okay. Okay, so find the 23rd term of the arithmetic sequence. So of the two, the one that I would use would be the first one. And the reason why is we know the first term. They gave us the first term. Okay, so I'm going to be using this one. The one we just proved. All right, now we have to know the a sub 1, but we also have to know the common difference. So again, it might be hard to see from here to here what's going on, but from here to here, it looks like I'm adding 5. So now I can kind of think, does it look like I'm adding 5 here? Does it look like I'm adding 5 here? And it does. So our common difference is going to be 5. Okay, so we're ready to substitute in everything that we need. So we're trying to find the 23rd term. So n is going to be 23. A sub 1, we already know, is -8, and n is 23. And then the common difference is 5. All right, so we just got to do the math. So let's see here. 23 minus 1 is 22. And then 22 times 5 is 110. So it looks like we're going to get 102 for the 23rd term. Now, if they gave you small enough, like they said, find the 8th term, well, you could just be like, well, you had 4 more blanks, just keep adding 5s, you know? But 23 is a big enough number to where, like, okay, maybe I'll actually use this formula to get it. Okay. All right, the next one. Now they kind of flip things on us. We're not going to be using the formula in the same way we used it for our last example. We are still going to use that formula, but just in a different way. So remember, we already knew that a sub 1 was -8, and we knew that the common difference was 5. Okay. But they're telling us which term is 247. So that's going to be our a sub n. It's going to be, we don't know what n is, but it's going to be our nth term. Okay, so we're going to substitute these all in. So we're going to have 247 here. A sub 1 is -8. We don't know what n is. That's what we're trying to find. It says which term is 247. You know, I'd like to know if I knew n, let's say it was 8, then I would be able to say, oh, it's the 8th term. Okay. And then the common difference is 5. So the first thing I'm going to do here is add 8 because I'm trying to get n by itself. So 247 plus 8, 15, carry the 1, 255. And I'm going to do something different than what we're used to. Normally we would think to distribute there, but I'm going to divide by the 5. So I think that's going to get us there faster. So, let's see here. 5 goes in 51 times. And then we'll just add 1. So we get that. It would be the 52nd term. So no way would I be doing that by hand. I'd have to get so far down the line before I could figure it out. So I'm glad I have these formulas. So 247 is the 52nd term. All right. Now this one, I can tell that I'm not going to be using that first formula because that first formula depends on knowing a sub 1. In this example, they give us the third term. Okay, so let's say we just kind of draw out my sequence here. We know that the third term is 8, right? Okay, and then we know further down the line, but I'm not going to go all the way to the 16th. I don't feel like drawing that many blanks. Okay, so I'll just do this. We know that the 16th term is 47. So anytime they give you two terms and it's not the first term, right? That's when you're going to be using the other formula. Oops, either. Instead of n minus 1, n minus n. Okay, and now remember, if I want this to be positive, n has to be bigger than n. So this, the bigger number, is always going to be the n, and then the smaller number is going to be the n. So when I substitute this in, it should be a sub 16 equals a sub 3 plus 16 minus 3. And then times the common difference. So we don't know. So the last problem. Okay, so just making sure that when you subtract here, you get a positive number. So that tells you n has to be the bigger one. Okay, so let's substitute in a sub 16. A sub 16, oops, sorry guys, is 47. So we're going to put 47 in here. A sub 3 is 8. And then 16 minus 3 is 13. So we'll go ahead and take away 8. 47 minus 8 is 39. So we'll just divide by 13 to get that d equals 3. So we have the common difference, okay? And now they want us to find the first term. So honestly, the easiest way, remember the common difference is what we're adding each time. So we would say, okay, well, we're going to add 3 to get from that term to the other term, right? But another way you could think of it is if I was going this way, I would have to subtract 3. So it should be 5 here. I'd have to subtract 3 again. So it should be 2 here. So that'd be what I would say would be the quickest way to find it. But let's say it's really far along the line and it's not just the third term, but it's like way further out. Then what you would want to do is you would want to revisit this formula, the one that has a sub 1 in it. That makes sense because a sub 1 is what we're trying to find. And you could either use a 3 or a 16, doesn't matter. Let's say I use 3 because I think the math would be easier. So I'm going to use the third term. We know the common difference now, so let's plug it in. Now the third term is 8. 3 minus 1 is 2. And then 2 times 3 is 6. So when we subtract 6 from both sides, there's the 2 that we knew was the answer for a sub 1. Okay. All right, so this is a pretty famous formula. I hear different books saying that that Carl Friedrich Gauss, came up with this formula at different ages, very young. Okay, I've heard kindergarten, I've heard second grade. So somewhere in elementary school, he came up with this formula. The rumor is that his teacher, that he was just really annoying, and his teacher was giving him busy work because he was smarter, than a lot of the kids in class at math, at least. And so she's like, here, go add the first 100 numbers. This will keep you busy for a while. And that's how he came up with this. So the formula is right here. This formula helps us add up the terms of a sequence, okay? The first n terms of a sequence. So let's go ahead and use it using his logic, and we'll show you kind of where this formula comes from. So to find the sum of the first n terms, you're just going to have n divided by 2 times a sub 1 plus a sub n. I always say the first plus the last. Okay, so let's see here. Find the sum of the first 100 numbers. So this would have been how he did it. So what he's trying to find is this. Oops. I want to do 8, 9, 11. So what he did is he actually wrote the series backwards. 100, 99, 108. And this would be 3, 2, 1. And then he said, well, I'm going to add downward. And he noticed that no matter what, he always got 101. No matter what. And this is only, this only occurs, this is an attribute only for arithmetic sequences. If you try this with some other type, like a geometric or something, you will not get this happening, but you get the same number every time. So the question is, okay, I just need to add a bunch of 101s. Okay, so how many of these 101s are there? Well, there's one for every number from 1 to 100, right? So there should be 100 terms, right? So he just has to do 100 times 101 to find the sum for that. Now, don't forget though, the only issue is that's not your answer, because we actually added it twice, because we added it onto itself backwards. So this is really double what we want. So don't forget that when you get done, you do need to divide it by 2, okay? And so if you look at this and you compare this to the formula that he has given us, the formula looks like this, right? Okay. Well, and this is for S sub n. This means that I'm summing the first 100 terms. So that there should be, like in this case, right? There should be 100 here, which there is. Now this 101, if I break it down and show you where that came from, where we came up with the 101 is we added the first term, which is 1, to the last term, which is 100. So we added the first term to the last term. And that's clearly what you can see right here, the first term plus the last term. So really cool how he came up with this. Anyhow, we should probably go in and get the number, right? Okay, so I'm just going to bring this down. So 100 divided by 2 is 50. And we have to do 50 times 101. So 50 people actually. I'm embarrassed. The math teachers, I feel like I should know it. All right. So pretty cool. Very interesting. So what we'll do from now on, though, is we'll just use the formula he got for us now that we understand how he got it. Find the sum of the first 15 terms. Okay, so I'm going to write down the formula. Okay, so n is going to be 15, which means n here is 15. And then the first term is clearly going to be 4. But the problem here is that we don't have the last term, huh? We don't have the 15th term, okay? So right now we're looking for a sub 15. So we're going to have to do a little detour here, right? So detour, this formula will help us find the 15th term. So if we want a sub 15, a sub 1, which is 4, n is 15, so we want the 15th term. And the common difference, it looks like we're going up by 3 every time. So the common difference is going to be 3. So this gives us 4 plus 14 times 3. 4 plus 42. Which gives us 46 for the 15th term. So now we're ready to go substitute it in. So the sum, the 15th partial sum, or the sum of the first 15 terms, 4 plus 46. So 15 over 2 times 50. And 2 doesn't go into 15, but 2 does go into 50 25 times. So we just have to do 15 times 25. So the sum of the first 15 terms is 375. There we go. Okay, so two formulas in one there. Okay, so using sigma notation, can you find the sum? So the first thing that I would ask you to verify is this even arithmetic? Because remember, I can only use this if it is arithmetic. So you might go in and find a few terms, right? You might say, okay, well, what happens when I substitute a 1 in, right? What happens when I substitute a 2 in? What happens when I substitute a 3 in? So 8 minus 5 is 3. 8 minus 10 is -2. And 8 minus 15 is -7. So these are the numbers in the series here. And so what happened to get from here to here is we went down by 5. And you notice we went down by 5 again, okay? So this is indeed arithmetic. You do want to check for that. Otherwise, using this formula would be completely bogus. You couldn't just use it on like any old sigma notation, okay? Remember we said a second ago when Gauss came up with this and he reversed it, that adding downward and getting the same number every time is only an attribute of arithmetic sequences, okay? All right, so what we're missing though is we are missing the last term. We know the first one, right? And so basically, let's go ahead and fill in the formula as much as we can. We're trying to sum up the first 22 numbers. We can see that from our lower and upper index, okay? So we're trying to find the sum of the first 22 numbers, okay? So n is going to be 22. And we know the first is 3, but we don't know what the last is. We don't know what a sub 22 is, right? So we're going to have to substitute in 22 to find out what the very last number, right, in this series is. So let's go ahead and substitute in 22. This will be 8 minus 110, which gives us -102. So forget the plus sign, it's going to be -102. So we have 11 times -99. And so that's going to be, gosh, I think it's going to be 1089, but trust me. Very cool. So let's just go and double check here. So 11 times 99, no, it's negative. It is 1089. Okay. All right, so trick E. First is arithmetic, and I need the first, so plug in the lower number, and I need the last, so plug in the upper number. Now, just a comment, if they don't start at 1, let's say it starts at 3, then you're going to plug 3 in to find the first term, okay? You're not going to substitute a 1 in always. You're going to plug in whatever this lower index is, and that's going to be your first term. Okay, so now we're going to look at both formulas in the context of some word problems, okay? So we have a stack of electrical poles. There's 5 poles in the top row. The second row has 6, the third has 7, and so on. There are 26 rows. So kind of what I'm sensing here is like, okay, the first row, let me draw that more straight. The first row has 5 poles. It sounds like they're giving me a sub 1. The second row has 6 poles. And the third has 7, and so on. And we know that there are 26 rows total. So it says how many poles are in the 26th row? Well, that sounds like it's asking us for the 26th term. Okay, so let me kind of write this out. Use a little bit smaller font so I can fit a lot of words here. Okay, so asking how many poles are in the 26th row is the same as asking for the 26th term. And why am I writing this down? Well, we have 2 formulas. So we have to see, am I going to be using the one that finds the nth term, or am I going to be using the one that finds the sum? Well, I want to find the nth term. So let's use the formula. Okay. All right, so in other words, This one right here. And I'm using this one because I do have a sub 1. So that's why I chose that one. All right, and we want to find the 26. The first term is 5. 26 is n. Now, what's happening each time is that it looks like we're going up by 1. We're adding another pole in each row. So our common difference is going to be 1. So we have 5 plus 25 times 1. So in other words, we have 5 plus 25. So it looks like there's going to be 30 poles in the 26th row. Let me just stare at that and make sure I did everything okay here. Looks good. All right, cool. So we got the 30. All right, now there's a second question. It says how many poles total? Okay, so when it says how many poles total, that sounds like it wants us to add up all the terms, right? Okay, so asking how many poles total is the same as asking, let's just say, yeah, is the same as asking us to add up all terms. Okay, so we're going to use the sum formula. Let's use the sum formula from Gauss. All right, so in other words, this. Okay, so we got to find the sum of 26 terms. There's 26 rows. We know the first has 5 in it, and we know the last has 30 in it. So 26 divided by 2 is 13. This will be 35. So we just need whatever 13 times 35 is. $55. So got everything that we needed. And this one, it's almost the same thing. It says an outdoor amphitheater has seating in concentric semicircles. So this would be like the first row. This would be like the second, etc., right? Circles, half circles. Okay. Actually, it would go all the way here, huh? Okay. All right. This one would be the third. So the first row has 11. The second row has 16 seats. The third row has 21 seats, and so on. And we'll just, it says there's 24 rows. So there's going to be a 24th row. But we don't know how many seats are in it. That's what we're supposed to find, huh? Okay, so finding how many seats are in that row is the same as finding out the 24th term. So I'm going to write down, here's a sub 1, right? A sub 2, a sub 3, like that. And then we want to know how many seats are in the 24th row. So we're going to start off by using the nth term formula. I'm not trying to add them all up. I'm just trying to find how many are in that last one. Okay, so we want the 24th. So n is 24. We know a sub 1 is 11. Now the common difference each time, well, it looks like we're going up by 4. No, by 5 I can add. Yeah, by 5. So the common difference is going to be 5. So we've got 11 plus 23 is 5. We got 11 plus 115. So we have 126 as how many seats would be. And that's 24th row. All right. First part solved. Now, if the amphitheater charges $80 per ticket, how much money in revenue was made for a sold out event? And this, I've actually done this. My husband and I used to make my husband go to a lot of ballets with me because I used to do ballet. And so we'd be sitting in there, you know, maybe it'd be the Dorothy Chandler or there's the one in Orange County that we go to a lot. You'd be like, I wonder how much money they're making because there's so many people in a ballet company, you know, and even people behind the scenes too, not just the dancers. Like, man, they can't be making a lot of money. So we'd sit there and we'd think, how much are they pulling in, you know, for the packed sold out event? And so we'd actually have to do something like this, like count the first row, see the difference in the seats from row to row, you know, count how many rows there were, you know. And it's kind of complicated because it changes how much it costs depending on where you're seated and stuff. So I don't know if we ever actually we got to estimate, you know. Anyhow, so let's see here. This one wants us to find out how much money and revenue is made for a sold out event. So we got to figure out how many seats there are all together. So in other words, we need to add up all the rows. So we're going to be using the sum formula. My husband used to fall asleep there. It was like a nice environment for him to close his eyes and check it out. All right, let's see. S sub 24. Okay, so we got 24 divided by 2. We know the first row has 11. We know the last row has 126. So this is going to be 12 times 137. So let's go figure out what the sum of the first 24 is. So 12 times 137. 1,644. Now, that's how many seats there are, right? But if it's $80 a ticket, then we're going to have to multiply, dollar sign. We're going to have to multiply $80 times the 1,644 to see how much money they made in revenue. So times 80, 131,520. Yeah. Okay. All right. Last problem, and a very important one if you are job. So it says Donna must choose between 2 job offers. The first job pays 60,000 for the first year with a raise of 2,500 each year thereafter. The second job pays 50,000 for the first year with a raise of 3,000 for each year thereafter. So you can see the dilemma. One of them starts off high but doesn't give as much of a raise. The other one starts off lower and gives a higher raise. So she wants to know if she plans to stay at the same job for 20 years, which job is the better offer? So the first thing I want to ask myself is, do I need to find the 20th term? Or do I need to find the sum? Let me put it this way. Do we need the 20th year's salary? Or do we need the sum of all 20 years salaries? And that's what I would labor over for a second. So it just says which job is the better offer. Well, I don't think just finding how much she's going to be making that last year is going to tell me which job's the better offer. I think the one that's going to give her the most money overall throughout all of the years is the best. So my answer to this question is we should find the sum of all 20. Okay. Okay, so let's go in here. For the first job, for job number 1, it starts off with 60,000. So they're basically giving you a sub 1, like that. They're giving you a sub 1. And each year it's going to go up 2,500. So that's going to be a sub 2, etc. The thing that we're missing, though, is we're missing the 20th, right? So let's go ahead and use this formula. And we want the 20th term. Well, the first term is 60,000. We know that there's 20 terms. And the common difference, well, it's going up 500 every year. And I'm just going to put this into the calculator. So 60,000 plus that 20 minus 1 is just 19. So 19 times 2,500. This is going to be for the 20th year, 107,500. Okay. Okay, but let's go and find the sum now. So the sum of all 20 years, that should accept this job. So that, oops, let me write it more, the formula down first, you guys, just to ground us. Okay, so S sub 20 is 20 divided by 2. The first year she makes 60,000, and then the last year she makes 107,500. Just gonna, you know what, we might as well make that guy a 10, huh? 20 divided by 2 is 10. So let's go see 60,000 plus 107,500. Gonna be, I don't know why I just didn't do that in my head, 167,500. But when you multiply by 10, it's going to tack an extra 0 on. So we are looking at her making 1,675,000 at job 1. Okay, we'd have to do the same exact thing for job 2 now. So for job 2, it pays 50,000 the first year. And then it goes up by 3,000. The second one would be 3,000. Again, what we're missing is how much is she going to be making that 20th year? So we're going to use this formula, rinse and repeat from what we just did, guys. All right, so we want the 20th term. The first term this time is 50,000. It's still going to be 20 minus 1, but the common difference this time is 3,000. All right, so I'm going to go put that into the calculator. So 50,000 plus 20 minus 1 is 19 times 3,000. 107,000. So she is not making as much. Oops. In that 20th year. So she did not, I think we can already tell the answer, you know, like if she was making 107,500 the 20th year, and she was making more money the first year too, I mean, clearly this job is better. But let's go ahead and find the sum just for the heck of it, just to get the practice. But yeah, she needs to go with job number 1. So in this case, I guess finding the 20th term would have been enough. So maybe in hindsight, find the 20th. Since this one started off with more, if on the 20th it's still more, then surely it's going to be a better job offer. But let's say that like you started off at 60, and then this number here, the 20th year, is less than the 20th year here. Well, then that's when you got to start looking at the sum. I'll do the sum just for the thoroughness, but you know, I think we've got it, guys. Okay, so we want to know the sum of the first 20. So 20 divided by 2, we already know it's 10. Okay, and then the first year she made 50,000, 107,000. So that's going to be 157,000. So if you add another 0 to it, 105, 4 zeros. So this would be, sorry for the small writing, I'm trying to fit all this math in on this small screen. A little bit less. So she should go with job 1. All right, you guys. So I put a lot of word problems in just because this is really fruitful and very useful. And I also really wanted to make sure that you could understand, well, when am I looking for the nth term versus when am I looking for the sum of all n terms? Okay, so that's something to think about anytime you come across a word problem. All right, take care, you guys.